Okay, folks, we can get going. Any questions from anyone about this week's checkoff? Things seem to be going relatively smoothly thus far in lab. I'll just remind you that you're integrating 2 demos in lab this week. The animation demo, which you're changing so that it's a ball bouncing off of a peg, and then you're bringing in a DMA demo. And as always, or as is usually the case, the first step of that integration that I recommend is that you get the 2 operating in the same program, but wholly independently. And so the DMA channels are chained together and they're just producing that tone like they do in the example by themselves. And meanwhile, the animation is occurring. And once they're working independently together in the same program, then integrate them. That would be my recommendation. Anything that anyone would like to talk about related to that? Be happy to if folks would like to. Bruce? Oh yeah, when you are doing this integration, remember that the DAC has 2 output channels, output channel A and output channel B. In the first lab, we just happened to use output channel B, but for no good reason really. And the DMA demo, I believe, uses the other output channel. And so in the event that you aren't hearing anything come out of that DMA demo and you're not sure why, just make sure that you are looking at the correct output channel of the DAC. Okay. Anything else from anyone? Incidentally, I think we resolved that VS Code nonsense from earlier this week. I posted a thing on Ed, and so if you're still having trouble, let me know, but that seems to be all resolved at this point. So what I would like to start doing, the piece of Lab 2 that we have yet to discuss, and that I feel like it's important that we do discuss, is the VGA driver that you are all using. And the reason that I think it's important that we discuss this is your goal in this lab is to get as many balls falling through that Galton board as you can. One of the things that you'll definitely want to do in order to get the most balls falling through the Galton board that you can is overclock the processor, which on the RP2040 is actually, the SDK makes this incredibly easy, and ultimately I'll show you how to do that. But when you overclock the processor, you do have to make an adjustment to the VGA driver because your system clock has increased so that the VGA timing is still correct. And so ultimately, I'd like to build up to a discussion of how you do that. In order to inform that discussion, we have to talk a little bit about how this VGA driver actually works so that you can understand the modification that you're making. In order to talk about how the VGA driver works, we have to talk about these PIO coprocessors. The other reason that I think it's a good idea to talk about this is some of you, depending on how efficient your code is, may find that your limiting resource for your number of balls is not in fact time, but memory. You may run out of memory to hold additional ball state. If that's the case, you may make the observation that about half of your memory, well, let's see, we're using 4-bit color. It's a 640 by 480 screen. And so that means we're using 1 byte for every 2 pixels. So that's 307,000 divided by 200 pixels divided by 2 bytes. You work that out, it's about half your RAM is being devoted just to holding color information, 4-bit color. Now, if you're okay with a slightly less rich color palette in your Galton board, maybe you're okay with a Galton board that's just black and white, you could reduce that to 1-bit color. And then in the same byte, instead of holding color information for 2 pixels, you can hold color information for 8 pixels. Which radically drops the amount of memory that you're using for VGA color information and frees up more memory for more balls in your Galton board. So in the event that you find that you're memory constrained, an understanding of how to modify this is going to be really important so that you can drop the memory consumption of the VGA driver. Sacrificing color resolution in the process, but kind of who cares, right? There's no requirement with regard to color for this lab. So I need to talk about the PIO. In order to motivate this conversation, I thought we would look just for a moment at how a VGA screen is actually driven. And I want to just talk about this a little bit so that we can discuss the utility of doing this in PIO. So how does a VGA screen work? Many of you at this point have hooked up the VGA screen already. And if you did, you will have noted that there's 3 color inputs, R, G, and B. And then there's 2 timing inputs, H-sync and V-sync, and then of course you ground it. And the VGA pin has a bunch of other connectors that we aren't actually using, but the ones that we're using are H-sync, V-sync, R, G, and B. In order to write a frame of information to the VGA screen, what happens is the following. Let's suppose, it's sort of a circular process, as you could imagine, because the screen refreshes. But let's suppose that we are in the process where we are about to write the first pixel, pixel 00, to the screen. In order to write pixel 00 to the screen, we set the analog voltages on the R, G, and B input to whatever values we want in order to generate the color that we want for that particular pixel. So I'll just remind you, we're controlling the R, G, and B inputs to the DAC from GPIOs, so they're digital outputs, right? For R and B, where we only have one bit, the consequence of that is the analog voltage on that input is either fully on or fully off. The green one, we have two GPIOs going through that resistor DAC, so that gives us the freedom to set the analog voltage on that input to the VGA screen to either off, a little bit on, a little bit more on, or fully on, right? You have 2 bits of resolution with regard to green. But in any case, we set the R, G, and B color inputs to the VGA screen, and then one VGA clock cycle later, we adjust them to the color that we want for the pixel immediately to the right of the first pixel. And then one VGA clock cycle later, we adjust it again the whole way across the screen, and that VGA clock is running at 25.172 megahertz. Turns out on our VGA screens, you can get away with 25 megahertz. And so our VGA driver is actually running at 25 megahertz. But different screens, I have discovered, have different sensitivities to this. So in any case, at 25 megahertz, we're adjusting R, G, and B the whole way across this screen. When we get to the end of the first row of pixels, R, G, and B go low. The H-sync timing input, this is a digital input, remains high for an additional 16 clock cycles of that 25 megahertz clock. It then pulses low for the H-sync pulse of 96 clock cycles, goes high again for 48 clock cycles, and after the VGA screen has seen that H-sync pulse, it knows, okay, I'm supposed to move to the next row of pixels. And then we, at 25 megahertz, we adjust the inputs to R, G, and B, go across this row of the screen, the second row, H-sync pulses again, and so on the whole way down through every row of the screen. When we get to the bottom, very analogously to H-sync, the V-sync control input, timing input, remains high for an additional 10 line times for the VGA screen, pulses low for 2 lines, pulses high for 33 lines, and the VGA screen, after seeing this V-sync pulse on its V-sync input, knows, okay, I got to go back to the pixel 00, the top of the screen. So you'll notice a few things about this protocol or this standard. The first is there's large sections of time here where we are not actually drawing anything to the screen. At the end of every line, right, we spend the active part of the line drawing pixels to the screen, and then for an additional 16 plus 96 plus 48 VGA clock cycles, we aren't actually drawing anything. And then at the end of the frame, for an additional 10 plus 2 plus 33 line times, time to go the whole way across the line, we aren't actually drawing anything. Does anybody have any guess as to why this would be the case? This is actually a history question. We talked about how there's some historical artifacts associated with like the UART standard that connects back to teletype machines. There were some matters of inconvenience with teletype machines. It is the time it takes for the electron beam to go back to the other side of the screen or to go back from the bottom corner of the screen to the top. So this is a relic from back in the day when these screens had a little electron beam scanning across the back of it, interacting with the phosphor, surface. And because this is an actual physical beam that was moving, when you got to the end of the line, you actually had to move that beam back to the other side, which took non-zero time. And then likewise, when you got to the bottom of the screen, you actually had to move it back to the upper left of the screen, which took non-zero time. And so these blanking regions, to my understanding, are artifacts of how those screens used to work. So if we want to use a microcontroller to generate this control input, What does that require? It requires that we have the ability to adjust the outputs of our R, G, and B pins at precisely 25 megahertz. This is very sensitive to timing, so we have to adjust those R, G, and B outputs at exactly 25 megahertz. And it furthermore requires that we have exquisite timing on our H-sync and V-sync inputs, right? I'm just pointing this out to hopefully make the point that if you were trying to do this from your application code, you probably could. It would take a lot of work, and what it would probably end up costing you is a lot of CPU time, because these are very timing-sensitive processes. So whatever your application is doing, controlling this screen from your application code would have to take highest priority. It would have to interrupt whatever else was going on, whatever video game you were trying to implement or animation you were trying to do. Just getting something on the screen would have to take precedence over that and interrupt whatever process you were trying to actually, whatever graphics process you actually wanted to do a lot. And so you would lose a bunch of CPU time just to controlling this thing. This is the motivation for us for driving this screen from this peripheral that I'm going to describe today and over the next couple of days, these PIO coprocessors. What these allow for us to do is do all of this highly timing sensitive control input to this screen completely using peripherals that are outside of our CPUs, outside of the ARM processors. The consequence of this is your ARMs, your application code, does not even know that this control input is happening. It costs exactly 0 CPU time for our RP2040s using our VGA driver to control this screen and get stuff to go up. The interface to the screen from your application's perspective is an array. There's just an array of characters in RAM, in global space, and if your application code wants to write a particular color to a particular pixel, it goes to the index of that array that is associated with that pixel and writes the value to that index that assigns the color that you're interested in. Just by writing to that array, then in the background, a DMA channel comes in and moves through that array, grabs information out, and whisks it off to these PIO machines that are controlling the VGA screen, so that when you change the value at that index, the color that you asked for just appears at the right place on the VGA screen. And so to your application, writing to the VGA looks just like changing the value of an array. And so if you were to look more closely at that draw pixel routine, for instance, what you'll find if you look at that is all that it's doing is looking at the pixel that you want to draw, using that pixel to compute which index of that array it should go to, and then looking at the color that you want to draw and writing that value to that index. And that's it. Okay? Again, this is to motivate why the PIOs are so interesting and so useful. This would be really, really, really hard to do without these things. You could probably do it. This has been a project in this class in previous years for previous microcontrollers where people got to control a VGA screen from a microcontroller. Just getting the screen to work was the success, right? And there was very little CPU time left over to do anything. This frees up all of our CPU to do, in your case, a Galton board. Does that make sense? So let me talk a little bit about these PIOs. I want to spend a little bit more time talking about them in the abstract because they are so sort of unique as far as, to my knowledge, there is no other microcontroller with a peripheral like these. And so I think it warrants a little bit of extra abstract discussion. But let me just remind you, I'm showing you a picture of this block diagram that we've looked at a number of times. This comes from the data sheet. And I'll just remind you that here on this block diagram, here's where the PIOs are represented. You can see that there are, in fact, 2 of them, PIO 0 and PIO 1. The data sheet calls these blocks. There's 2 PIO blocks. The green coloration here is to indicate that each of these PIO coprocessors, PIO peripherals, have access to all of the GPIOs. And so from these peripherals, we can control all the GPIOs. And as we'll discuss, each of these are completely separate coprocessors that we program them separately. We write programs for each of these in an assembly language that we'll discuss. But they have some really interesting features. So we can talk about this in a few layers of abstraction. There's 2 of these PIO blocks. What I'd like to do is let's zoom into one of these and look at the stuff contained inside one of these PIO blocks. So inside of each of these PIOs, there can exist up to 4 state machines. The datasheet calls these state machines. You can think of each of these state machines as independent programs. They could exist entirely independently of one another. There also do exist some signaling mechanisms that allow for state machines within a single PIO block to flag one another. The datasheet calls these interrupts, but they don't really act like interrupts. They act more like flags. So you could have state machine 3, for instance, send a signal to state machine 2, and state machine 2 could react to it. But each of these state machines you can think of as its own program. Now, in order for these programs to be useful, we have to actually be able to communicate to them from our application code running on the ARMs. So connected to each state machine, there are 2 FIFOs. One FIFO goes from the ARM, which would sort of live over here through the bus, it sits between the ARM and this state machine, and it sends data in this direction. This is the TX FIFO, the transmit FIFO from the perspective of the ARM, transmitting stuff into the PIO. Each also has a second one, the RX FIFO, that allows for the state machine to shuffle data back to the processors. So it's through these FIFOs that we can send information from the ARM to these state machines and retrieve information from these state machines back to the ARM. The CSDK includes functions that allow for you to do this from your application code if you wanted to. So you could call a function called something like PIO state machine 1 send and put a value there, and your code would then pop whatever value you placed in the argument into this FIFO. The more powerful way to interact with these things is all of these FIFOs are visible, they're all memory mapped, and so we can point DMA channels at any one of these. And so if you have a DMA channel facilitating communication between these state machines back to whatever process you're running, the bandwidth that you can achieve between state machines and your application code is tremendous. You can, at very, very high rates, shuffle data from memory, say a pixel array, over to a state machine that's running, say, a VGA driver. Right? So you could have that DMA machine shuffling stuff over at 25 megahertz. Or alternatively, if your state machine is sucking information in from the GPIOs, you could be retrieving that information extraordinarily quickly. See what else I want to say about this. So as designed, what these are really optimized for is highly specialized digital interfaces, high speed, potentially wide in the sense of like lots of GPIOs involved, very high speed digital interfaces. And part of what gives them that specialization is they're extremely deterministic in the sense that each of the instructions, which we're going to look at here in a moment, there's 9 of them, each of the assembly instructions with which we can program these state machines is guaranteed to execute in 1 clock cycle. So if your RP2040 is running at 125 megahertz, 125 million clock cycles a second, and you have a state machine program that includes, I don't know, 5 assembly instructions, you can guarantee that those instructions will execute 1 cycle, the next cycle, the next cycle, the next cycle. Yes?
Sorry if I missed it. What does PIO stand for?
You didn't miss it. I forgot to mention it. Programmable I/O. Programmable input-output machines. So the consequence of this guaranteed single-cycle execution is it allows for you to answer questions like, let's say you had a state machine program that was just sort of running independently. That is to say, it wasn't stalling on any signals from the FIFOs or anything like that. And you started it, and I asked you, what line of this program will be executing in 1,200,356 clock cycles? You could tell me very quickly. So you know exactly what line of code will be executing on exactly every cycle. As I sort of alluded to, you can introduce some non-determinism here because you could have your state machine stall until it's signaled by your application code, for instance, or it could stall on a GPIO or something. But you have the ability to set up a highly deterministic program. Those kinds of programs I typically only associate with FPGAs, stuff like that. And so there's a number of sort of cool opportunities that these PIOs introduce. One is it makes the RP2040 a reasonable substitute in some applications for an FPGA. I can give you an example of this. A couple of years ago, I worked on a project with Professor Lal, Amit Lal here. He was working on a very specialized camera. Basically, it takes pictures of stuff that's really close, right? So it's this very, very high-speed, highly specialized camera that you could, for instance, push into the dirt and it images like nematodes. It's very cool. It has this tremendously high-speed digital interface, 30 GPIO inputs, and those need to be toggled to 5 nanosecond precision, right? So we're driving this thing at 200 megahertz. They were driving it, of course, with an FPGA. Over the course of about a year, we were able to replace that FPGA with an RP2040. The FPGA cost $500. This cost $1. Right? It's really interesting in that it makes this little $1 microcontroller a reasonable substitute for a device for some applications where really the only other reasonable device for a long time was something much, much, much more expensive. The other opportunity that this presents, and if I had to speculate, I think probably the reason that Raspberry Pi would include something like this is when you are choosing a microcontroller for your project, you're probably basing that decision on a number of different things. Power consumption might be a concern for you. But one of the things that you're certainly looking at when you're picking a microcontroller is the suite of peripherals that it offers. If you know, for instance, that you need to communicate with a bunch of different SPI devices, you probably want to look for microcontrollers that have SPI peripherals. Likewise for UART channels or I2C channels or whatever it may be. With these, let's say 2 SPI channels weren't enough for you. You just build yourself a bunch more out of PIO. You write your own SPI driver that looks to your application code like just another SPI peripheral. So if you need a third, you build a third. If you need a fourth, you build a fourth. If you need another UART channel, you build yourself a UART channel. We'll look at all of these as examples, by the way. Or alternatively, let's say you want to use a microcontroller to control some device that is a little bit unusual and that you wouldn't expect for microcontroller manufacturers to spend the time and energy and money to build in as a default peripheral in these things. Say, for instance, a VGA driver. Well, this allows for us to just build our own custom peripheral to talk to that specific thing that we want to talk to. The VGA is a good example. Another example might be if folks have done projects with those long LED strips. You may know that the control interface to those LED strips looks like square waves where you're adjusting the size of each square wave in order to affect the color of the strip. You can bit bang that for certain, but you could make a really rather simple PIO program that just makes a highly specialized interface for controlling LEDs. I've used a PIO peripheral to build a CAN interface into the RP2040. Controlled Area Network, I think is what this stands for. This is the bus that implements data flow in like a lot of vehicles, forklifts and cars and airplanes, to my knowledge, and that kind of thing. You're unlikely to find a microcontroller with a CAN peripheral built into it, but with the PIO, you can build your own CAN peripheral, your own custom peripheral into these things. So that's part of what makes them so interesting. In any case, so we've got these 4 state machines. The other thing that I'll just mention, so I mentioned that we can communicate back to our ARM through these FIFOs. Each state machine is also capable of generating interrupts. And so by way of those signaling flags that I was talking about that facilitate interstate machine communication, a subset of those flags can also throw an interrupt to the ARM so that the state machine could make an interrupt service routine run on the ARM side. We can look at examples of that as well. Now, here is what is, in my opinion, the most fun part of working with these things. These 4 state machines on a single PIO block share instruction memory. And the total size of the instruction memory is 32 instructions. So that means the sum total number of lines in all of the programs across these 4 state machines, if each line contains one of those 9 assembly instructions, that program may not exceed 32 lines. It's an awesome constraint. Okay, so these end up looking like little poems, right? There's very few lines there, and so to the extent that the length of a program is, they're simple programs in that they're short, right? But with very few lines, as we'll see, you can generate a ton of complexity. And so it's an awesome exercise in very, very constrained engineering. You only get this many lines of code. So given some goal protocol that you want to achieve, VGA or CAN or LEDs or whatever it may be, you have to achieve whatever you're trying to achieve in less than 32 lines of code per PIO block. There's 2 PIO blocks. Yeah.
Why wouldn't the instruction memory be larger?
That's a good question. I don't know. Bruce?
So this is optimized for speed, means it has a limited address code read, and there's 5 addresses. The other question is, for a real application, let's say a new SPI channel, how many instructions does it take? 3.
We'll look at an SPI implementation here, but 3 instructions. So like I said, as of now, this is unique to the RP2040. If I had to bet, I will bet that peripherals like this become more common. I'll bet, because they're so useful. Oh, there you go. Okay. So I'll just remind you, we have 2 PIO blocks. This is what lives inside of each of those PIO blocks. The last zoom in that I'd like to do is I'd like to take a look at what is contained within each of these state machines. So 2 PIO blocks, each contains up to 4 state machines with their own FIFOs and so forth. Each state machine only contains the following. Within each state machine, you only have 1, 2, 3, 4, 5 registers. You have 2 scratch registers, scratch X and scratch Y. As their name suggests, these are just scratch registers. You can put information there while you're doing something. I don't know, decrementing a counter, for instance, to count instructions or whatever it may be. But you have 2 scratch registers. You have a program counter. The program counter is just keeping track of which line am I presently executing. So in the absence of a jump instruction, which we'll talk about, which allows for you to adjust this program counter sort of conditionally, in the absence of that, this program counter will start at the first line of your program, counts up to the next one, next one, next one, next one, and when it gets to the bottom, it goes back to the first and counts up again. But as I sort of am suggesting, you can play games with this. We'll talk about that in a moment. And then there's 2 registers that are connected to those FIFOs that go out to the ARM. One is called the output shift register, which connects to the TX FIFO. And so if we want to pull data into our state machine from the TX FIFO, that data, by way of an instruction that we'll talk about, ends up in the output shift register. Likewise, there's an input shift register that has a connection to the RX FIFO. So if we're sending information back to the ARM, it will go through the input shift register and out to the RX FIFO. There's a clock divider here. And so what this, I mentioned that each of these instructions has guaranteed single cycle execution, but maybe you don't want to be executing instructions at full system clock rate. Maybe instead of executing instructions at 125 megahertz, you want to execute them at 25 megahertz, 25 instead of 125. You could divide down the PIO clock so that you slow down your PIO relative to the system clock. And then there's some control logic here as well. Anything else to mention about this? Again, it's very simple in the sense that there's not a lot going on in here. Inside of each one of these state machines, so associated with each one of your little programs that you write, your programs are only going to be manipulating 1, 2, 3, 4, 5 registers, right? And then as we'll talk, some of the instructions will allow for you to control the flow of your program, okay? But all you're really doing is moving information between these registers, from these registers out to the FIFOs or in from the FIFOs, and you're gathering data from the GPIOs or putting data out to the GPIOs. And then, of course, you could implement some logic to manipulate the data in transition, but there's not much going on in each of these state machines. Questions about this? So the next thing I'd like to discuss, like so many things in this class, this stuff starts to make sense as you start looking at programs, right? And so, like we did with other things in this class, my strategy here is I want to present the system and present the instruction set, and then we'll look at some programs and see how it's used, and then we'll come back and look at the instruction set again, and we'll look at the data sheet, and we'll bounce around a little bit. But like so many things, it feels like a lot of information all at once the first time you see it. As we turn the crank a few times, it makes sense when considered all together. So let's look at those instructions. I mentioned that there's 9 of them. And you can think, so there's 9 instructions, but I would say these instructions really only fall into one of 2 categories. Let me look at this slide. All of these instructions really only fall into one of 2 categories. One of those categories is a set of instructions to move data from one place in here to another place in here, to move data from the TX FIFO into the output shift register, to move data from the input shift register to the RX FIFO, to move data from scratch X to in, right? So there's a set of instructions that exist just to move the data from one place to another place. The places where data might be moving to and from include the FIFOs, the registers, and the GPIOs. So we'll talk through these in detail, but one group of them just does that. And then another group of them controls program flow. So it allows for you to say, you know, when I get to this line, subject to some condition, please jump over these lines of code to this set of code down here. Or it allows for you to, you know, program things like, please run this section of code and then jump back to the top and run it again n number of times where you specify n, and then move on. And so there's a subset of these instructions that's just moving data, and then a second subset that is just manipulating program flow. So let me talk about each of these sort of at a high level, and then we can look at some of the details of them. But there's a jump instruction. All that the jump instruction does is take the program counter, and rather than incrementing to the next line of code, it asks a Boolean question. It checks a condition. It could check a condition, or it could be unconditional. And it will jump that program counter to someplace else in the code that you specify. We'll look at what those conditions could be, but all the jump instruction is doing is what the name perhaps implies. It allows you to jump elsewhere in your program. Once you've jumped there, the program counter starts incrementing again as usual, until perhaps it hits another jump instruction, at which point it goes elsewhere, or it hits the end of your program, at which point it wraps to the top. Okay? But you can jump. So that would fall into the category of program flow. The other instructions that would fall into the category perhaps of program flow include the wait instruction. Wait says, please step through my program, and when you hit the wait instruction, stall. And when some condition is met, and you get to specify what that condition is, we'll look at what your options are. When that condition is met, then continue on. So you could, for instance, wait on one of those interrupts from another state machine, those flags that they can signal back and forth to one another. And so if state machine 1 is running and it hits a wait instruction, it could wait until state machine 2 signals it, and then the 2 are synchronized. Right? So this is a mechanism, for instance, for synchronizing between state machines. You could alternatively perhaps wait on a GPIO going high or low. Let's say, for instance, that you are building a PIO implementation of a SPI channel. Perhaps you could have your PIO state machine stall on the chip select line, doing nothing, and when it goes low, everything starts. Or a UART channel. If you're implementing a UART interface, maybe you wait for the start bit. So it allows for you to stall your program until some condition is met. The IRQ instruction is the mechanism by which your state machine generates these flags, right? So state machine 1 could throw an IRQ that is observed by state machine 2 to synchronize, as I mentioned. It's through these IRQ instructions also that each state machine can generate an interrupt back to the ARM. Okay, so you could think about these as flag mechanisms, it's IRQ, which is sort of affecting program flow. And then all the other instructions, which I'll talk through in a high level in just a moment, are just moving data around. Okay, so for instance, the in instruction there, you can see that the in instruction specifies a source and a bit count. The in instruction just says, please move data from my specified source. Perhaps your source is the output shift register, the scratch X, the scratch Y, the GPIOs. Move data from the source that I specified to the input shift register. So the destination for that instruction is the input shift register. And you can play some games with this, like saying, please only actually move 2 bits from the scratch X register into the input shift register. But fundamentally, it's just moving information from some source that you specified to the input shift register. Similarly, there's an out instruction where you specify the source, or I'm sorry, the destination where you would like for the data to go, and the source of the data will be the output shift register. So if you say, oh, out X, what that means is please move data from the output shift register to the X scratch register. And here too, you can play games with number of bits. Out X2, please move 2 bits from the output shift register to the X scratch register. There's in and out, which moves data into the input shift register or out of the output shift register. There's push. Push moves data from the input shift register out to the RX FIFO. So you hit a push instruction, that's you pushing data out to the ARM. Pull pulls data from the TX FIFO into the input shift into the output shift register. So the ARM sends us some data that it would like put to the GPIOs according to the protocol that the PIO is implementing. That appears in the TX FIFO. We suck it into the state machine and serialize it out the GPIOs. So that's in, out, push, pull. Move, as the name perhaps suggests, allows for you to specify a source and a destination. And it says, please just move whatever lives in the X scratch register or the Y scratch register or whatever my source is to wherever my destination is. Your destinations could include any of the 5 registers here. The destinations might also include the GPIOs. You say, please move the contents of the X scratch register up to 32 bits to the GPIOs. Bang. And then all 32 of those bits toggle the GPIOs. You can even do wacky things like this. There's the move instruction and the out instruction and a couple of the others. They allow for you to specify one of the destinations that you can choose for the contents of one of the registers is the syntax is exec, exec. What that means is please take the contents of my specified register, interpret it as a command. Right? What this table is showing us is that each of our instructions here is just a 16-bit number. This table is just telling us what each bit in that 16-bit number represents. So if we have a 16-bit number in, say, the Y scratch register that is properly formatted as an instruction, you can say, please take the data in the Y scratch register and execute it. You can imagine that this could get pretty twisted, right? So move, and then the last one that I'll just mention is set. Set's a little bit different, where you specify a destination, X scratch register, Y scratch register, shift registers, whatever, and you specify the value that you would like to write to that register, subject to a constraint, which is visible in this table, that the data payload here is only 5 bits wide. And so that means with this set instruction, you can only write information to these registers, set information to these registers, to values that are as large as 31, but no higher. In the event that you wanted to initialize one of these register values to a number bigger than that, you'd have to come up with some other mechanism of getting that number into that register. For instance, you might have the ARM pop a big old number into the TX FIFO, execute a pull instruction to pull that number from the TX FIFO into the output shift register, and then perhaps you do a move X out instruction that says, please take the contents of the output shift register and move it to the X scratch register, and now you've got a big old number in your X scratch register, right? So you got to play a little bit, a few games here. Yeah?
So there's only a 3-bit opcode, you have 9 instructions, because push and pull in the same opcode, but then use bit 7 as like a 4th opcode bit?
Yes. Yes, precisely. So, other questions? Yeah. You can, and actually that's a good segue. The question was whether you can increment or decrement. Let me just pull up the data sheet here quickly before we go look at the code. So in the data sheet, all of chapter 3 is PIO. Well written, as this whole data sheet is, and worth reading. but we could jump down here to the instruction set. Here's the table we were just looking at. And then in the data sheet, for each instruction, there's a more verbose explanation than I just provided for that instruction. So let's start, for instance, with the jump command. I mentioned that you can jump subject to some set of conditions. So you hit the jump command, it checks if a condition is satisfied, and only if so, then it will execute the jump. Otherwise, it passes right through. So what might those conditions be? One condition is no condition. That's a unconditional jump. Every time you hit that jump instruction, just go to wherever I told you to go. Or alternatively, you could say, please only execute a jump when the X scratch register is 0. If there's anything in the X scratch register, don't jump. Or to answer your question, this is pretty interesting. The condition could be only jump if the X scratch register is non-zero prior to a decrement. And so that jump instruction, jump X minus minus, what that says is execute the jump if the value in the X scratch register is non-zero, and then after you checked that, decrement that value in the X scratch register. So this is handy, for instance, if you want a section of code to execute some number of times, you could initialize the X scratch register with the number of times that you would like that code to execute. You go into that loop of code, execute, 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 hit the jump X minus minus instruction. It says, is the X scratch register 0? Oh, it's not. Let me jump back up to the top of that code, and I'll decrement it when I do. And after you've counted off the number of times that you want to execute it, it falls right through. You are then responsible for reinitializing the X scratch register. Yeah. So think about this. In one cycle, that instruction that I just mentioned is checking a condition, decrementing a value. We haven't talked about it yet, but you can set it up such that it can simultaneously also manipulate some GPIOs on the side. And you may have a specified delay in there as well. That's like 5 things that single instruction does in one cycle. I don't know exactly how that works. Do you have an idea, Bruce? Okay. So in any case, this is where you'll find more information about each instruction. I just wanted to briefly point to a few of these. So, you can jump and decrement. You can do the same things for the Y scratch register. You can jump in the event that the X scratch register's value is not equal to the Y scratch register. You can jump on a pin in the event that the pin that I have specified is high or low. Please do a jump. Actually, just high, as far as I understand. You could also jump on the content of the output shift register. In the event that the output shift register is not empty, jump. This is suggesting applications in which, for instance, the code that you're repeatedly executing is emptying the shift register, right? And you keep going through that code until you've emptied it. So lots of conditions under which you can jump. It also tells you what the instructions look like. Wait, like I suggested, you get to decide, do you want to wait for a 1 or a 0? And then do you want to wait for a 1 or a 0 from which source? You could wait on a GPIO. You could wait on a pin that you've labeled as being the pin that you're waiting on. You could wait on one of those interrupts from another state machine. The wait instruction also has some other handy features. You could say, for instance, where is it? I can't find it written here. It's somewhere here. I'm just not seeing it. What it allows for you, let's say you're waiting on an interrupt, waiting for it to go high. The wait instruction can automatically clear the interrupt when it goes through, which is a good mechanism for synchronization. Yeah. Uh-huh.
Can the address be like an assembly label, or is it an explicit PC value?
Yeah, so that's a great question that's getting slightly ahead of where we are, but the programs that we write, which we'll look at in a moment, they include the instructions, of course, and then you can also include program labels. And so you can do a jump to a label, and under the hood, what it's actually doing is substituting in the correct program counter. Yeah?
So do labels kind of look like macros?
Yeah, sort of. I think that would be an appropriate sort of mental model for this. Yeah. But you don't have to explicitly write the numeric value of the program counter for a jump, though you could. So some more information on jumps, more information on wait. The in instruction, as I suggested, you specify the source and it moves wherever you specified as the source, the contents of that to the input shift register. Those sources could include the pins, the X scratch register, the Y scratch register. Null, that just means move all zeros in. The input shift register, the output shift register. And you also get to specify how many bits you would like moved. Anything else to mention here? Out is sort of analogous in the opposite direction. Push and pull. I want to, there are a few sort of extra configurations that I want to speak to a little bit before we get into the code. We don't have much time. Let me just sort of allude to them for the time being. I mentioned the clock divider settings already. This allows for you to slow down the PIO state machines relative to your system clock. Auto push and auto pull. We can look at this in the data sheet in a moment, but let me just sort of speak to it for a minute. On both the input shift register and the output shift register, there are shift counters. And so if you say, please move 1 bit from my output shift register to, say, the pins, it will increment the shift counter by 1. If you move 2 bits, it'll increment the shift counter by 2. And so it's shifting the data out 1 bit at a time or n bits at a time where you specify n. Auto push and auto pull allows for you to tell the system when you have counted a certain number of bits being shifted out of the output shift register, say, please automatically execute a pull instruction. So I'm not going to explicitly write a pull instruction. I want for you to count the number of bits I've shifted out of this register, and when it hits the threshold that I specify, 8 for instance, then automatically go do a pull of go pull from the TX FIFO back into the output shift register. So this is a mechanism, and then analogously in the opposite direction for the pushes, right? When I've counted a certain number of bits coming into my input shift register, automatically do a push to the RX FIFO. So auto push and auto pull saves you a single pull instruction or a single push instruction in your PIO programs. When you only have 32 instructions to spend, you care about being able to save these individual instructions. Okay, so that's a mechanism by which you can do that. FIFO joining, the TX FIFO and the RX FIFO, each of them are 32 bits wide, 4 samples deep. If you're writing a program where you're only ever going to be sending data from the ARM to the PIO machines, say for instance a VGA driver, you're only ever sending data that way out to the pins, you can join the 2 FIFOs so that you have a single 8 sample deep FIFO in one direction. Pin mapping for each of those instructions that can touch the GPIOs, right? So for example, the in instruction can touch a GPIO, please pull in from the pins. The out instruction can push out to the GPIOs. The move instruction can move information from a register to the GPIOs. Set can also configure the GPIOs. For every instruction that can touch the GPIOs, you get to configure which GPIOs you're talking about in connection with that instruction. If you say set pins to, you clarify in the configuration of the PIO program what pins you're talking about when you say set the pins to 2. And you can have different GPIOs mapped to different instructions. So if you say move the contents of the X scratch register to the pins, those pins could be a different set of pins that you're talking about than when you say set the pins to some value. You can be talking about different sets, or they can be overlapping. They could be talking about the same pins. There's some constraints with this that we'll talk about when we look at the code. Side set is a feature that I alluded to. For each instruction, you can simultaneously with that instruction be executed, you can say that you would also like for up to 5 pins to change their values in a way that you specify. So you could say, for instance, set X to side 1, and what that would mean is, in this cycle, please set the contents of the X scratch register to 2, and at the same time, go to the GPIO that I've configured as the side set GPIO and set it to 1. Those two things happen simultaneously. This is really handy for things like an SPI channel, where you want to do things like read in data from the data line and also simultaneously toggle the clock. The side set allows you to do both these things at the same time. I think this will become clear when we look at this in code. I just want to tease it a little bit. And then wrapping, the last thing I'll mention before we close for today, I mentioned that each of these programs goes from the top to the bottom. Maybe there's jumps, so maybe you move around a little bit. But when you get to the bottom instruction of your program, it loops back up to the top and then just starts going through again, right? So it executes in a cycle. Wrapping allows for you, let's say that your program had some set of instructions that you only want to execute once. Maybe you're initializing register values or something. And then there's another set of instructions that you want to execute over and over and over again for the duration of the program. One mechanism by which you could do that is with a jump instruction that takes you back to that section of code and unconditionally jumps over and over again. To save you that jump instruction in the event that you can't afford it, wrapping allows for you to set a target wrap point so that when you get to the bottom of the program, you say, please don't go to the top, please go to this wrap point that I've specified, so that it doesn't wrap all the way to the top, but instead just wraps in that section of code that you want repeated over and over and over again. So auto push and auto pull are for saving you a push instruction or a pull instruction. And wrapping is to save you a jump instruction. So like I said, this is a lot of information very quickly. As with everything, I hope that this will become clear as we start to look at some simple examples and then some more complex examples. My goal here is to start with very, very simple examples of this, and then over the course of 1 or 2 lectures, we'll build up to the VGA driver so that we can look at it, and at that point, these PIO programs will look like old friends. You'll be able to, okay, I see what's going on there, right, in connection with the VGA standard. So that's the plan. I'll be in lab this afternoon. I'll see some of you then. I'll see the rest of you on Monday.